Okay, in this next section, we're going to look at the mathematical form of the potential function. Just like in that last one, we looked at the mathematical form of the potential energy. We're now going to look at the potential, not the potential energy, but the potential, and they're different. Remember that the potential energy only exists in the last section between two charges, but the potential exists everywhere in space. And it's really a very, very neat concept. The potential is expressed by the symbol V. This is the electric potential. And the electric potential at a given point is the work that I would do, the potential work that I would do to put a charge Q naught at that point R. So if I have a whole bunch of charges, I can say, what's the potential right here? The answer is, I've got all of these charges glued down. Some are positive and some are negative. And then I drag a charge in from infinity and put it right at that point, and it's a charge Q naught. I figure out how much work that took, then I divide by the charge. So the potential is the work for a unit charge, whereas the potential energy is just the work that I need to collect the charges. Now, one of the differences is the potential energy requires that I have some charges there, whereas the potential existed everywhere in space, whether there are any charges there or not. And so it's a very useful concept. And as I said before, this is going to be measured in joules per coulomb, and that has the units of a volt. And a volt is something you're very familiar with. It is the electric potential. It is the pressure that you have in your wiring system that wants to push the electrons through a light bulb or through a vacuum cleaner or something like that. You should remember that for a battery, for regular batteries that we have, that's AA, AAA, C, and D batteries, that you have a 1.5 volt potential from one end to another. Now, what does that mean? And a 12 volt potential for your automobile. Well, let's just take a battery. This might be a D battery, so it's 1.5 volts. And we ask the question, this is the positive end, this is the negative end. And if we took a negative charge down here of 1 coulomb and ripped it off the bottom and brought it up here and pushed it onto the top, that work of 1 coulomb over 1 volt, 1.5 volts, would be a voltage of 1.5, and that would equal to the work that we do, the potential, divided by our charge, which is 1. So it would take 1.5 joules to do that. In other words, a battery has a voltage of 1.5 volts because it takes, for a 1 coulomb charge, 1.5 joules to move a charge, that unit charge, from one end to another. If we think of a car battery, which has the two ends like this, and there's a 12 volt difference, then to move a 1 coulomb charge from one battery terminal to the other takes 12 joules. 12 joules. Now, a problem that I might give on the test is we take a car battery, and we're going to move 7 coulombs from the positive 7 coulombs from the positive terminal, from the negative terminal to the positive terminal. How much work is done? Well, the answer is, we know that the work that we're going to do, U, is going to be the charge that I move times the potential, or the voltage that I have. So it's going to be Q times the voltage. And so that's going to be equal to our 7 coulombs times the potential difference, or the voltage, which is 12. So it'll be 7 times 12, 7 times 14, 84 joules. And that's the work I would have to do to move the 7 coulombs of charge. Remember how useful that potential is, because it's not a vector, so you can calculate things very easily. It's how much work I would have to do if I were to move something. Potential energy is how much I've already done in making a particular configuration.